Here I have a beach ball Earth. Now I'm rotating it in the proper direction, and this is what we see, or why we see the stars rise in the east and set in the west, just like we see the sun rise in the east and set in the west. Conceptually, if you want to look at it this way, let's see if I can do this. If a patch of sky is here, and we're looking at the United States, this is a patch of sky. Now I'm going to rotate through the night. That patch of sky, that didn't go so well. That patch of sky is visible for a period of time, and then the Earth points away, and then it becomes visible to the other side of the world, like China, and now the United States is facing away. So this is kind of the loose, a really rudimentary example of the Earth's rotation, and it rotates about this axis. So what we observe on Earth is we actually tend to view it as a big sphere around this whole thing, where all the stars and all the planets reside along that sphere. Even though the distances to the stars are very, very, very far apart, our intuition would say they are spheres. In fact, for thousands of years, that's what they thought. They thought that everything revolved around the Earth, that it didn't spin, that the Earth was just fixed, and then that sphere just rotated around the Earth. When in reality, the Earth spins and the whole sky spins about its axis. So, what I have pre-drawn already here with my rudimentary artwork is kind of the main concepts that we will be talking about regarding the celestial sphere. So, this sphere would be somewhere out here, and I'm going to talk about a couple of key points here. One, the North Celestial Pole, and another, the celestial equator. The celestial equator, if you can imagine, taking the equator of the Earth and extending a plane out into space until it meets that celestial sphere, where for a long time people thought all the stars were just on that sphere, until it meets that. This is still, even though this model is no longer correct, it's a great learning tool for understanding where you are in the night sky, understanding the seasons, understanding the motions of the sun and the stars. So that's why we're going into this concept here. So the Earth spins, would go this way, sorry, and it spins this way, so it appears that this whole sphere would, the whole outside sphere would spin around it. We'll get deeper into that with your labs when you go into Solarium. You can actually watch the night sky do this from various locations on Earth. So what I want to talk about necessarily here is how your observation changes according to your locations. For instance, we are lucky enough to have the North Star, which is Polaris. Polaris happens to be right on the North Celestial Pole. The Celestial Pole comes from the North Pole, essentially, or the rotation axis, and it extends all the way until it hits the sphere, and you got to think of maybe Polaris being on the sphere out here. Okay, the South Celestial Pole exists, but we're not going to concentrate on that too much. I shouldn't say exist, because these are imaginary concepts, imaginary lines that we draw. But this is a good thing. These are two definitions that are key to know. The North Celestial Pole, which extends from the North Pole out into space until it hits the sphere, and the celestial equator, which extends out from the equator. Now I want to talk about a little bit about difference for what an observer sees depending on where they're located on Earth. As you go more north, you'll see that something quite different happens. So I'm going to draw some people here in three positions here, and hopefully I won't mess this up because I drew such a pretty Earth. But let's say we have a person standing here at the equator, and it looks like they're just standing kind of in the middle of the ocean, the way I've drawn this. We have another person standing here, which is in between the equator and the North Pole, and we have another person standing here at the North Pole. So let's consider these three situations. I'm just trying to see if that shows up pretty good on the screen or not. I don't know, they kind of look small, so let's try to make this guy a little bit bigger. All right, so the observer here, and let's just get this a little bit more accurate. The observer here at the equator, let's just talk about the line of sight. The horizontal line of sight, so looking that way, and the vertical line of sight, which actually points to your zenith, which I'll talk about in a second. But you got the vertical line of sight and the horizontal line of sight, which I'm going to draw in red here. So a person here this is their horizontal line of sight. This is their vertical line of sight. Okay, so I'm just using red dots here. The person standing here, this is their horizontal, and this is their vertical. And likewise, up here. So a person standing here is going to look this, when they look straight up, they are going to see the celestial equator. So a star in the celestial equator, which you don't know a whole lot about yet, but the celestial equator, there are certain stars that will reside in the celestial equator, but they'll be looking right at it if they are standing at the equator and looking straight up. So this is their line of sight vertically, and this is what they see. Horizontally, what they see is the perspective would actually be kind of flattened here, so they would see Polaris along the horizon. So they're standing there, they look up, they see the celestial equator. They look that way, or they look towards the north. The north is from where I'm at, it's technically that way. They look towards the north, and they see Polaris even with them, so like on the horizon. Okay, and we'll talk a little bit about the horizon in a second here. Here, a person, let's go to the other extreme case before we talk about this person. Here at the North Pole, the person's line of sight horizontally now is going to see the celestial equator, because they're standing here, right? They look to their sides, and what they see is exactly the celestial equator. They don't see anything below that. They see only the northern half of the celestial sphere. So at the horizon is going to be the celestial equator, because this is parallel with the celestial equator. So that's what they see on the horizon, is the celestial equator. When they look directly upwards, they look right at their zenith. What they're going to see is the star Polaris here. Now those are the two extreme cases, and they're kind of easier conceptually to understand. But let's talk about an observer in between this location and that location. So in between the celestial equator up to the North Pole. So as the observer goes more and more like this, you would think, because Polaris is directly on the horizon, that it gets higher and higher in the sky until it's overhead. So that's, as you go more and more north, the higher Polaris gets in the sky, because Polaris is fixed, because this celestial pole never changes. The axis is always the same. It's always, the Earth is always rotating around this axis. So Polaris is always essentially in the same location. It's off by like a slight degree, but it's, for all practical measures, it's right on the celestial pole, so it's nice to see. So a person like this doesn't see Polaris directly overhead. They see it, they don't see it on the horizon. They see it sort of in between. Like if I was to trace this line of sight out, they would see it somewhat above their horizon. And same with celestial sphere, they would see it somewhat above, or the celestial equator, they'd see it somewhat above their horizon. So I'm going to talk a little bit more about this. This is a really crude drawing as far as the scale goes and everything. So that's not, so don't let that confuse. I'm just trying to indicate here that Polaris gets higher, and it comes somewhere in between as you go more north. At first, it's on the horizon because it's parallel with Polaris, because these are parallel. And then as you go more north, Polaris gets higher in the sky. Similarly, when you're at the North Pole, this line of sight here is parallel to the celestial equator, so the more you go south, the higher the celestial equator gets in the sky. It's kind of weird conceptually at first, and the more you work with it, the more you'll get familiar with it, and we'll have plenty of chance to do that with the lab, and we're using Stellarium, and it'll be a pretty cool demonstration. So I'm going to talk about maybe this observer and sort of a different way to think about the celestial sphere. So this would be like the hemisphere of the celestial sphere. Let me just tilt this a little bit. This would be the hemisphere, the upper northern half hemisphere of the celestial sphere. So going back to this thing, it would be the sphere that extends out to here from the celestial equator up into the North Star. So this is essentially this is the horizon. Okay, so this is like this is the hemisphere that local observers see. Sorry, I think I messed that up actually, because really, you know, the actual half of the celestial sphere is actually this half right here, because this is the celestial equator here, which I'm going to talk about. So this would be an observer at like 30 degrees latitude. So on my Earth or whatever, I've gone up like maybe to here. So an observer may be standing maybe somewhere in Texas here or something. An observer standing in there at 30 degrees latitude. That's the location. So we're going to find a really good relation between latitude and latitude and Polaris, and latitude of where the celestial equator is. So a person standing here is going to see Polaris 30 degrees above the horizon at 30 degrees latitude. Now, 90 degrees from Polaris is the celestial equator. So they're going to see the celestial equator at about 60 degrees, because he's making a 90-degree angle. The total here is 180 degrees. But keep in mind, and a lot of people make this mistake, keep in mind that this on the horizon is 0 degrees. So I've labeled this, so on the horizon it's 0 degrees, so it goes 0 to 90, and then it goes back down to 0 from there. It doesn't go from 0 to 90 and keep going all the way up to 180. It goes, that's a kind of a concept that a lot of people struggle with. They fail to remember that. This degree marking is how high above the horizon it is. So, a couple other points to talk about here. The celestial equator, and for this location, it doesn't exactly go straight up and down. So it rises in the east and makes a path towards the south and more vertical until it hits the meridian. The meridian is an imaginary north-south line that runs from north directly to south. It's an imaginary line that divides the sky into eastern and western halves of the sky. Again, this is better to show with stellarium how that actually happens. But the meridian here, which I've defined here, is actually just this line right here. Although if I turned it, you'd actually see that there was some space there. But there's a meridian here that's directly from north to south. Now, when a star is rising, say on the celestial equator like this, piece by piece by piece, it gets higher and higher and higher in the sky. That makes sense. You see stuff on the horizon rising, and it keeps getting higher. You go out a couple hours later, it's higher and higher, until it reaches that imaginary line called the meridian, which separates the east and west half the sky. The Earth keeps rotating at the same rate, so once it reaches that point, it's going to start getting lower and lower and lower in the sky again until it hits the horizon again. Now, the celestial equator, no matter where you are in the northern hemisphere, it's always going to rise exactly on the east and exactly on the west, because you're really just tilting that globe, essentially. So in this case, even though this is not quite 60 degrees, if I were to rotate this and you could look on the other end, it would be less than 60 degrees. When it reaches that meridian point, that's when it gets to its highest point at 60 degrees. So one other thing maybe I want to point out is I've indicated the zenith here. So looking straight up, that's where my zenith is going to be. So when we use the term zenith, that's what we're talking about. That's at 90 degrees altitude. That's the maximum altitude. As far as altitude is defined, that's the maximum it can be, is 90 degrees. It can never be more than 90 degrees. It can only go from 0 to 90, and then from 90 to 0 again. And that's the same if I were to look at it from this direction, and all the way up to 90, and all the way to the other, pointing towards the east there. In every direction, it can only go from 0 to 90 degrees. We tend to view the Earth as straight up and down. That's the way we like to picture it. That's the way our globes are. But you've seen probably globes that are slanted. But in reality, this axis here, so if I have an axis line here, if I have an axis line here, it's actually tilted 23 degrees. So the Earth is actually tilted, and it rotates about its axis, but in its orbit relative to the sun, it's actually tilted. And this is why we get the seasons, which we will learn all about. So over here, I have traced out a very good schematic for the Earth's revolution, which is different than rotation. Rotation is a spin about the axis. The revolution is its path around the sun for an entire year. So let's just start here on December 21st. This is the winter solstice. This is the shortest day of the year. This is the day that the northern hemisphere gets the least amount of light. Conversely, not to confuse you, in the southern hemisphere is the longest day of the year where they get the longest amount, or the most amount of light. But we only care about the northern hemisphere, right? Because we live in the northern hemisphere. And it's where the whole course is designed off it. So I've labeled the pole here north. You can see these kind of like poles here pointing north. So at this point, the winter solstice, that is the point in which the northern hemisphere is as far tilted away from the sun as it can be. That's just the northern hemisphere. If I were to actually talk about this would be the axis tilt would be relative to a line straight up and down or perpendicular to the sun. This would actually be 23 degrees that way. That's because it's the 23 degree tilt that I was talking about. Okay, and that has a number of consequences which we'll discuss and find out in the lab. Okay, so we move forward a couple of months, and we get to the spring equinox on March 21st, which we just had. When that happens, in the northern hemisphere, we start getting out of winter because the northern hemisphere gets more and more exposure to the sun as it comes this way, until this point in which we start to head towards summer. Now at this point, this northern hemisphere and the southern hemisphere are both equally pointed towards the sun. Neither one of them is pointed towards the sun more than the other. They're both getting equal amounts of sunlight on that specific day. So then as we go further and we get into summer here, then we have the northern hemisphere pointed towards the sun. And that's when we get to summer, because we get more direct light and longer days, which we'll talk about even further. So then this is on the summer solstice. We've gone through the winter solstice, spring equinox, summer solstice. So let's go all the way to the fall equinox yet. That's the last one we haven't gone to. And again, we get this even position. So now the northern hemisphere, instead of being pointed towards the sun the whole time, it starts to come even and starts to get pointed away from the sun after this point, and we start to head into winter. Because at this point, both the northern hemisphere and the southern hemisphere are getting equal amounts of light and energy from the sun. So then we keep going all the way to the winter solstice, and we've accomplished an entire year. There's more information on here. I've labeled some of the constellations that might be visible in those positions. So we've got Gemini in this direction, we've got Virgo in this direction, Sagittarius in this direction, and Pisces in this direction. So what is key about this? Let's start at this position, okay? If I'm an observer on Earth and I'm looking this way, if I look this way, the sun is going to be in my way. So all I'll see during the daytime is the sun. Any of the stars back here and over here, I won't be able to see them because the light from the sun will be filling up all the sky, and I won't be able to see the stars at all. I could remove the sun and those stars would be visible, but that would have drastic consequences on life on Earth. But the sun is pretty much taking away my field of view. So if I'm in December 21st and I'm looking at the night sky and I'm on Earth, in no way can I actually see Sagittarius, because it's only out during the daytime. So on December 21st, if I'm looking, I can only see Sagittarius. I can't see Sagittarius because it's blocked by the sun, essentially, or it's filling up the sky with light, and the sun is blocking that path. However, this would be the night half. This would be the nighttime side. So from here on over, this is all the night, and I don't have the sun in the way this time. So when I look this way on December 21st, I will be able to see Gemini. So the same thing kind of goes here. You can do all sorts of permutations like this. I could say, if I am at the spring equinox, okay, which constellation would I see? Would I see Virgo, or would I see Pisces? Well, in this case, the sun is in the way on March 21st. It lights up the whole sky. You wouldn't see Pisces. You would see Virgo because that area, you're looking directly into space away from the sun. Okay, I could do all sorts of permutations. I could pick September and ask the same question. The sun is in the way, so I won't see Virgo, but I'll be able to see Pisces. And similar with Sagittarius over here, the same kind of reasoning goes. So that's kind of a good thing to know as far as why different constellations are visible at different times of year. Because as I move here, they become less and less visible. As I get to this other side of the sun, suddenly the field of view of Gemini is cut off. As I get to September 21st, the field of view to Virgo is cut off. If I get to Gemini, the field of view to Sagittarius is cut off. Now, you might be thinking, as far as astrology goes, and I'm not into astrology at all, but some of you are. But astrology, this is kind of the idea here, is Virgo, the sun would be in Virgo on this day. And I think it's a month off from when they originally developed astrology, so if you're into that type of thing, you might be saying, wait, on September 21st, that's not a Virgo. I don't know, it could be. It's like right on the edge, I think. I don't know. But that's why they say that, because the sun is in that constellation. You can't see that constellation, but that's when the sun is in that constellation. So that's kind of where the idea of astrology comes. It's like your sun birth month or something like that, even though the Earth is kind of it wobbles over 10,000 year period, and it's actually shifted a month since then, so it's not quite accurate. So that's a little brief introduction on how the patterns of a year of the Earth's revolution around the sun 1 year. This is kind of the stuff that happens. Now let's just show you how that correlates to like path length on the when you're looking at it from a hemisphere, like I was talking earlier, where I was looking at the observer's hemisphere. So I'm going to take again an observer at 30 degrees. So I'm going to be at 30 degrees. Okay, so you have maybe this observer standing here. Okay, so now I want to talk about the sun's path length. Okay, so if I take, let's try to get this better here. If I talk about, let's talk about first, maybe June 21st. Let's talk about this position. This position where the axis is tilted this way. Okay, so where the northern hemisphere is pointed towards the sun. That's where we're going to start first. If you pay attention to the sunrise on that day, and you mark it right when it comes up, right at sunrise, it will be a little bit north of east. So it'll come up on the horizon here, and just north of east, and that's where it will start, okay? What you'll find is, and again, because of the location, and what you'll find here is that this is at 30 degrees. I'm going to quickly do this in my head here, 83.5 degrees. So it will actually cross the meridian, reach its highest point at 83.5 degrees. And we'll figure out why that is. Why would I know that it's 83.5 degrees? Why would I know that's the highest altitude of the sun? It's a really easy way to figure it out, but some people can get a little confused by it. So this is the point where it crosses the meridian, reaches its highest point in the sky, and then I watch it again until it hits west, and I mark where it is when it hits west, and it ends up hitting a little north of west. Okay, so this is in summer. All right, this is on the summer solstice, mind you. So this is this position right here, where the northern hemisphere is pointing most towards the sun, and this is a big reason why we have summer and seasons. This is one of the two big reasons here. So it comes here and it crosses the meridian at its highest point, and then I just trace that line until it hits that point just north of west when it sets. So this is the set, and this is the rise. Okay. So that's the sunset, that's the sunrise, and that is this is for June 21st. I want to talk about maybe the other extreme. Okay, so here's the other extreme. You have the winter solstice. And on the winter solstice, as it turns out, the sun doesn't rise exactly due east or exactly due west, just like it doesn't in summer. It actually rises a little south of east. So a little bit south of east is where the sun will rise, and then it will come up to, actually, let's make this a little bit more stream, and it will, the suspense is killing you, isn't it? It will what? It will reach 60 minus 23.5. It will reach 37.5 degrees. So about here, this is about 37.5 degrees here. So this is on December 21st. So the sun comes, and then you'll find again if you follow it when it sets. So I'm going to get this last point. So you need 3 points: rise, cross the meridian, and then another point. So when it crosses the meridian, at its highest point on that day is at 37.5 degrees, and then it sets again in the west. Now I'm not going to talk about the equinoxes. The equinoxes, it actually rises directly on the east and sets directly in the west, and it reaches 60 degrees here. I'm not going to talk about those. I'm just going to talk about these two extreme cases in winter and summer. Okay, so in summer, what can you say about this path length? It's obviously a lot longer of a path than it is. Well, maybe it's not obvious because I didn't do it the most accurate way, so let's just do it this way. This will probably make it more obvious. If I made, something down here, you can see that that's a really short path length. So as you get away from the center, you get shorter path lengths. So here's the key here. Here's the key. In summer, this is really long. In winter, this is really short. So you end up having shorter days in winter and longer days in summer. Now the effect of this is, you can see again that this is at its highest point. In summer, this is when it reaches its maximum altitude. The sun will always reach a point from here all the way a range until we get to summer, and then we'll go back towards winter, crossing the equinoxes back to summer or back to winter. So back and forth like this. It just does this all year round in your location. They're not always 83.5 or 37.5 degrees. It depends on your location, and again, we'll be able to experiment with that a little bit in the lab. My point here is that the sun is really high in the sky. Here, it's lower in the sky. So I don't really have a flashlight, but you can, you should mess around with this at home. So I'm going to use my phone here, and hopefully this will show up a little bit. So I'm going to use the flashlight here. So I can see if I'm pointing directly at the board, all that light is concentrated in a small area. So light contains a lot of energy, so this is actually focusing a lot of that energy right onto that surface. If I tilt it like this, then that same amount of energy, instead of being so concentrated, is spread out over this entire region. This is a huge, huge reason why we have the seasons. So in summer, you get focused light. In winter, you get more diffuse light. And we call that indirect, so this would be indirect light, and this would be direct light, because it's direct. And then indirect would be you're getting light, but it's kind of spread out a little bit. So a lot of people have the conception that the Earth is actually closer in summer and farther away in winter. In fact, this might be one of the things you can stump somebody with. It's actually closest to the Earth is actually closest to the sun at some point in winter. Okay, so I mean, just think about that logically. That wouldn't necessarily make sense, because then why would it be, if it was closer or farther away? Why wouldn't the whole Earth? Why wouldn't everybody in the southern and northern hemisphere have winter at the same time and summer at the same time? So that's just logically thinking about that. If it was actually closer or farther away, it's a very, very common misconception. In fact, I've seen videos where like Harvard graduates get this wrong on like 60% of the time, 60% of the students on the question. So going back, let's just talk a little bit about that direct light thing again. So first, we've got one of our first big reasons why we have seasons here. In the summer, the days are longer, and then the winter is shorter. So you get less sunlight in winter, more sunlight in summer, because it's out longer, you know. So now I want to talk about direct light versus indirect light. So if I've got let's say I've got a surface here, okay? And let's just tilt it a little bit, but keep the same amount, okay? Now let's just draw some light. This is always hard to draw, so I'm hoping I don't mess this up. They look about the same length. Maybe this is about the same length. So I take this surface and I tilt it. This is sort of like tilting my flashlight, or my phone light, if you will. This is sort of like that. So let's just say I've got these light rays coming in this direction. Okay. And I carry them through. So, just so I can see these two situations here. This is hitting directly. It's hitting perpendicular to the surface. So let's label that. Direct light. This is not hitting it directly, so this is indirect light. So again, let's just say we have 3 light rays. They contain a certain amount of energy. You have 3 light rays. They're coming and they're going to hit a surface. These are just like the 2 different cases, and I'm just kind of showing it to spread those out to see how so you can see how it spreads. In this case, all 3 are hitting directly, so you're getting the most concentration of light. When it's tilted, then you end up having this spread out, and the distances in between light rays become smaller. So you get a lot less indirect light, and so it spreads out a lot more. And in this case, if I took the exact same area, so these are actually the exact same length, I've just tilted it. It may not look like it. They look, to me, if I look at them closely, they look like they're pretty good same length. And I tilt it a little bit. Here I've got all 3 rays hitting it. Here I've got only 2 rays hitting it. So the direct versus indirect light is a very, very key factor as to why we have warmer summers and colder winters. Because in winter, when we're pointed away, like in this situation here, this situation is sort of like this situation here, where we're getting less rays and they're spread out. So they're not all not all that light is concentrated in one area. So that would be sort of the case, and hopefully my phone won't die, but that would be the case of where I have, hopefully this works, come on. Well, apparently it doesn't work. Well, I'm not going to record the whole thing over. So, but anyway, that was the case where I had it tilted and I had the area coming out like this. This would be the case where I had it pointing directly at the board and I had it concentrated right at the board. So that is the second main reason why we have seasons. So there are two. There's the direct versus indirect light. There's indirect light in winter, where in the summer it's direct light because the northern hemisphere is pointed towards there. You get a lot more direct light because you got that surface now pointing towards that sun, towards all that light, and you've got indirect light in winter where that light is spread out over that whole hemisphere. Okay, that's one of the big reasons, and the other big reason, as we talked about, was the length of days. So this is all caused by the excess tilt.
the axis tilt is the cause. So if you say, well, why are the seasons? Well, because the axis tilt. Well, that's kind of correct, but it's not really getting into the bare bones of what the effect is. And the effect are these two things, the direct light versus indirect, and the length of days.